So taking this idea of order versus chaos forward, we have this concept that scientists have named entropy. And the whole idea behind entropy is instead of trying to look at a system and asking, where's the energy, like playing a giant game of Where's Waldo, what we've realized is that the energy is always going to try and arrange itself in a more convenient way. Ultimately, that energy wants to spread out. So if I have a bunch of air molecules here, if they're in this tightly packed space, and then they can suddenly freely move around away from each other, they're going to spread out. We're going to have this giant diverse cloud of gas. So entropy is the study, it's the measurement of how energy is arranged in a system. And so when we talk about entropy and energy together, we're able to see that energy is always going to move in a way that makes it more favorable for entropy. So energy is always going to move in a way that's going to arrange itself in the most convenient way. And that happens because there's simply more options for it that way. Just like gas particles, if they're in a really tight and closed space, they only have so many options. But if they spread out, they have a lot more space, so there's a lot more options for them to go to. In the same way, as heat moves, it wants to move to a place where it has more options, where it's more likely to be. So when we looked at heat transfer, we saw that in a solid, heat is going to transfer through that in a straight line. It's going to move up the solid. That's going to happen because it's easier for the heat to move further to where there's less energy than it is to move backwards. It's like being in the lunch line. It's easier to keep going forward because the lunch line keeps going forward than it is to stop and turn around and go backwards. It's easier to just follow the flow. Energy is going to work the same way. And so this whole idea of entropy is really defined in the second law of thermodynamics. Let's look at that. So remember, the first law of thermodynamics is that energy cannot be created or destroyed. It can only change forms. That's the conservation of energy. The first law states energy is the thing that we can use to drive things, to move things, to make things happen. Well, we can't make more of it. We can't make less of it. We have the exact same amount. It can only move around. So how is it going to move around? Well, that's where the second law comes in. The second law is going to define how energy will move, and it's going to move according to entropy. The second law states that the entropy of the universe is always increasing. Now, this is actually really easy to see in our regular day-to-day lives. You look out on the road, it's starting to deteriorate. The road is breaking down. Without intentional effort from people, that road will break down. Look at our houses, our rooms. They steadily become more and more chaotic and disorganized over time. The second law of thermodynamics is telling us things will arrange themselves in a way that will increase the entropy. That will increase, another way to think about that is it'll increase how chaotic it appears. It will look less orderly. It'll move in a way that is more probable, that is more likely, that gives it more options. That's an easier way to think about it. Entropy is a very challenging concept that a lot of people really misunderstand. So just at a very basic level, as we understand it, entropy is just going to be how energy wants to arrange itself. And energy is going to be really lazy. It's going to want to arrange itself in the most convenient way possible. If I've got something like a very fragile stack of cards, it takes a lot of work for the energy to stay that way, and it doesn't really want to do that, right? It's just like it takes a lot of work to sit in a plank. You don't want to do that for very often. You'd rather just lay down. So energy is going to work according to entropy. That brings up the question, what about us? Well, I've mentioned without the intentional effort of humans, the road's going to break down. Well, what about the intentional effort of humans? Does that break the law of entropy? Well, as a matter of fact, in order for us to do work, we actually have to consume food. We turn chemical energy into heat energy, which increases the entropy. The work we do using food as a fuel source increases entropy more than fixing the road decreases it. This second law of thermodynamics also tells us how we can take advantage of energy. Because not only is it saying energy is naturally going to increase the entropy of the universe, it's also saying if I want to decrease the entropy somewhere else, if I want to make energy run backwards, I need to get some power to do that. The power to do that is going to be through a process that lets it run forward in a different way. So with that in mind, we can define how one of our processes works. Let's look at a refrigerator. So I've got a drawing of a refrigerator here. This is the front side, that's the back side. On the front side, all we see is the door. We can open it up. There's food inside. It's nice, it's fresh, it's cold. Outside, it could be 25 degrees Celsius, which is a very hot day. Inside, it could be only 3 degrees Celsius. Above freezing, but cold enough to keep our food from rotting. How does that happen? How do we keep it cold? Well, we know that the entropy's got to increase. So I've got thermal energy in this food. The energy, the temperature from outside the fridge wants to move into the fridge. And it's going to do that. A little bit of energy is going to leak into the fridge. So how do I get that energy out? Well, what I do is I pump something called a refrigerant through some piping. When I pump that refrigerant, it will actually get colder than the fridge is. I run it on the inside of the fridge, and I let the stuff in the fridge warm up the refrigerant. So, so I've got cold air in here, but it still has some movement. So I pump an even colder fluid through it. Put a fan on that to blow the air in the refrigerator around that colder fluid, and then I pump that fluid back out. So this is like if I just had a trail of ice cubes rolling through the freezer, and I had a fan that blew on the ice cubes so that all the air in the fridge blew across the ice cubes and got colder. And by the time they melted, by the time that the refrigerator got all of its heat absorbed by that ice, I pumped them back out of the fridge and then blew them off. So I've got a motor here. This is a motor that will pump this refrigerant through the refrigerator. On the inside, it'll allow it to expand so that it cools down. But on the outside, it'll compress it so that fluid heats up, and then it'll use another fan to blow the extra heat off. And then when it pumps it back through, it's lost all the heat from inside the refrigerator to outside the refrigerator. So how does that work? That's very complex. That might be hard to wrap your head around. But how does that work with entropy? Well, it takes energy. I have to run a motor and a fan with energy. I have to use electricity to do that. Well, the amount of electricity that I have to use to run this motor and to run this fan is using more electrical energy than thermal energy that's being moved out. So if I move out 100 joules of thermal energy, I might have to use 150 joules of electrical energy to run the motor. So the point here is that I'm using 50 joules more by allowing something to go to entropy. So that's how our refrigerators work. But there's one more word that we need to define in this. We've got entropy, which is a measure of how the energy in a system is arranged, how chaotic something might be, or how orderly it might be. And then we've got this idea of what things can just happen on their own. What things will happen? If I just take two chemicals, mix them together, and let them go, what, which ones will have a reaction? And which ones do I need to put some energy into? Which ones do I need to get started myself? The word for that is spontaneous. In chemistry and physics, the word spontaneous is used to talk about a process that can start all on its own, that doesn't need any help to get moving. A refrigerator running, that is not spontaneous. It will not naturally just cool the food down. That is not entropically favorable. It doesn't want to work that way. It will spontaneously, if I turn off the refrigerator, it will spontaneously come back up to room temperature and the food will spoil. So that is spontaneous. Spontaneous is all about what process will happen all on its own. A really good example of that is something like a cast iron pan. It's made of iron. If you leave it just sit and don't take care of it at all, it will rust. That is spontaneous. It will spontaneously rust. But if we take care of it, if we oil it and do what we need to do with that pan, it will not rust. So we need to put work into something to keep it from being spontaneous. And there are all these processes that we need in our lives, like the flow of electricity, that are not spontaneous. We make use of spontaneous processes, like a waterfall or the wind blowing, in order to get a non-spontaneous process. So we use spontaneity, we use something that will happen all by itself, and we tap into that power source in order to get the kind of energy that we want.